let's talk about something that happens to, well, pretty much everyone. Every time we try to measure something, anything really, the numbers are never quite perfect. There's always a little bit of fuzziness. So the big question is, how do we cut through all that noise to find what's really going on in our data?
So where do we even start? Well, to get right to the heart of it, all we have to do is ask a really, really simple question. I mean, you've totally been there, right? You step on the bathroom scale twice and get two different weights. You're trying to time something and the stopwatch gives you slightly different results each time. So, which number is the real one? Which one should you trust? That's the challenge we're going to tackle.
Okay, so it turns out not all errors are the same. On one hand, you have systematic errors. Think of these like a clock that's always 5 minutes fast. It's predictable, it's consistent, and you can usually adjust for it. But then there's random error. This is the unpredictable stuff, the little fluctuations that just happen. It's like static on the radio. And that's what we're diving into today, the wild and surprisingly orderly world of randomness.
Okay, so if we're stuck with all this random noise, how do we even begin to find an answer we can trust? Let's grab our first tool from the toolbox and figure out how to pull one solid number out of a messy pile of measurements.
And our first tool is something you definitely already know, the mean. You know, the average. You just add up all your different measurements, divide by how many you took, and voila. That number is our single best guess for the true value. It's the starting line for everything else we're going to do. But a best guess is only half the story, right? I mean, how good is that guess? Think about it. If all your measurements are clustered super close together, you're probably feeling pretty good about that average. But if they're all over the place, your confidence kind of drops. So the next big question is, how do we put a number on that feeling of confidence? And that brings us to our next big idea, standard deviation. Now, don't let the name scare you. Forget the crazy formulas for a second. Just think of it as a consistency score. That's it. If the score is low, it means your data is nice and tight. If the score is high, it means your data is all spread out. Simple as that. Okay, check this out. This is a perfect example. Look at these numbers for measurement set A. They're all over the place. We can calculate the mean, sure, but with a spread this wide, our consistency score, the standard deviation, is going to be high. And that means our confidence in that average is, well, it's not great. But now, look at this. Measurement set B. See the difference? It's night and day. Every single one of these values is packed in tightly together. The standard deviation here is super low, which tells us we can have a lot of confidence that our mean is really, really close to the actual true value. Okay, so now we have a best guess, that's our mean, and we have a confidence score, that's our standard deviation. And this is where it gets really, really cool. Because what happens if we don't just take 5 measurements, but we take dozens or hundreds? Something beautiful and totally unexpected starts to emerge from all that random chaos. So how do we see this pattern? Simple. We build something called a histogram. All we're doing is sorting our measurements into different buckets or bins, and then we just count how many numbers landed in each bucket. It's just a way to see our data visually. And take a look. Here's what happens with just 23 measurements. You can kind of see it already, can't you? It's still a little blocky, yeah, but you can see a shape forming. Most of the measurements are piling up there in the middle, and it gets smaller as you go out to the sides. So, that begs the question, what if we didn't stop? What if we took hundreds of measurements, or thousands, or 1,000,000? The more data we get, the clearer that picture becomes. And then, something amazing happens. Those clunky, blocky steps, they just melt away, and what's left behind is this perfect, smooth, elegant curve. It's the hidden order that was hiding in the randomness all along. And this beautiful, perfect shape, it has a name. It's called the Gaussian distribution, but you've probably heard it called the bell curve. It's this fundamental pattern that shows up everywhere in nature, and it perfectly describes how random errors tend to behave. But here's the thing. This bell curve isn't just pretty to look at. It's an incredibly powerful predictive tool. It lets us stop just having a feeling of confidence and start putting real, hard numbers to it. Because this shape is so consistent, so predictable, it gives us a massive shortcut. We can stop guessing about our data and start making very specific, quantifiable statements about what to expect. So here's the first rule of the bell curve. A massive 68%.
That's more than 2/3 of all our measurements are going to land within just one of those consistency scores, one standard deviation from our average. This is the sweet spot, the most likely zone for our results. Okay, but what if we go a little wider? Let's stretch that out to 2 standard deviations on either side of our average. Now we've captured over 95% of all the possibilities. This is a huge deal in science. If a result is inside this range, it's considered normal. And finally, 3 standard deviations. At this point, we're talking about 99.7% of everything. It's almost the whole shebang. Getting a result way out here by pure chance is unbelievably rare. So if you see one, that's a big red flag that something else might be going on. So let's just pause for a second. What does all this mean? It means that even when the world is messy and single measurements are uncertain, the way they're uncertain is actually predictable. And that predictability is what gives us a rock-solid way to be confident. And believe it or not, this is really just scratching the surface. There are even more tools out there for dealing with the real world, like special techniques for finding those weird outlier data points, or different rules you can use when you only have a tiny bit of data, and even ways to double-check that your data actually fits this bell curve pattern to begin with. And that's really what it all boils down to. Randomness isn't the same as chaos. It has a shape. It has rules. And by understanding those rules, the mean, the standard deviation, and the bell curve, we can finally find that clear, reliable signal that's buried in all the noise. So I want to leave you with a question. The next time you see a poll in the news, or you read the specs on a new gadget, or see a scientific study, and it has that little plus or minus number, now you know the story behind it. You know it's describing this hidden, predictable pattern in the uncertainty. How does knowing that change how you see the numbers that are all around us?